We just discussed the phenomenon of vapor pressure lowering, which happens in a solution when compared to the pure solvent. And interestingly, that particular result of the vapor pressure being lowered actually affects two other properties of a solution. And those properties are the boiling point and the freezing point of the solution. So, just a quick reminder of the definition of these two properties. Boiling point is a temperature at which the conversion of liquid to gas occurs. We usually specify the pressure at which this is supposed to occur. So we have a definition called the normal boiling point, which is when the vapor pressure of the liquid is equal to 1 atmosphere. So that's what we refer to as a normal boiling point. So that's when you see something boil, is when the vapor pressure generated by the liquid equals 1 atmosphere. That's for the normal. Otherwise, it would just be when the vapor pressure equals the external vapor pressure. The freezing point, on the other hand, is the conversion of solid to liquid occurring at, again, a specific pressure, usually defined as 1 atmosphere. Now, the interesting thing about the change in vapor pressure as a result of the addition of a solute to a solvent affects these two in the following way. The boiling point actually increases as a result of the change in vapor pressure, and the freezing point decreases. And so we call those boiling point elevation and freezing point depression. The way this happens can actually be visualized using a phase diagram, which, if you remember, is just a plot that shows the three states of matter that happens for a particular substance, with the y-axis here being pressure and the x-axis being temperature. A typical phase diagram looks something like this, and you have at high pressure and low temperature your solid, at high temperature, low pressure, you have your gas, and then your liquid is somewhere in the middle. And so what we want to see here is how the change in vapor pressure affects the boiling and the freezing points. Well, the vapor pressure, remember, is the line that is between the liquid and the gas state, right, which is this line right here. So if you think about it, it's this line that I'm coloring in blue in the phase diagram. Now, what happens to the liquid-gas equilibrium? Because the vapor pressure is lower, that number, which corresponds to pressure, is going to be lower than it was before. So in the solution, the vapor pressure is given by this dotted line right there. Okay, so this is vapor pressure of the solution. The blue line there is the vapor pressure of the pure solvent. Now look at what happens when the vapor pressure decreases for the solution. It intersects with this line, which is the solid gas equilibrium at this point. And then so if you use that to extend to the same with the same slope, this solid liquid equilibrium line, you get this other dotted line. Okay, and the reason that dotted line is important is because of a couple of things. One is that where that 1 atmosphere pressure intersects, this was originally the freezing point of the pure solvent. But you can see what happens is now, because of that new dotted line, the freezing point has been moved to the left of the original freezing point. So that means the freezing point of the solution is less than the freezing point of the pure solvent. On the other side of the plot, where we saw earlier that decrease in the vapor pressure of the solution, where that 1 atm intersects with the original plot, that's the boiling point of the pure solvent. But because the vapor pressure has decreased, now the intersection of the 1 atm pressure with the line occurs here, where the dotted line is, and that is now the boiling point of the solution. Okay, so you can see the boiling point of solution is higher than the boiling point of the pure solvent. And so this is what we define as both of those colligative properties, which is the freezing point depression, which is the decrease in freezing point of solution compared to the solvent, and the boiling point elevation, which is the increase in boiling point compared to the solvent. We can actually calculate both of these changes using the following equation. So for the boiling point, the equation is just simply delta TB, which is the change in the boiling point, equals to Kb times molality of the solute. So Kb here is a constant. I'll show you a list of these constants in a second after I show you the formula for the change in the freezing point, which is just Kf times molality of the solute. You can see that these two equations look very identical to each other. The only thing that differs is really just the constant that's being used. Okay, so the constant is a property of a solvent. So depending on the solvent, some solvent is going to make a bigger change or a smaller change in that vapor pressure, which then causes the change in the freezing point and the boiling point to be either larger or smaller. So these are some standard solvents that you might see being used with the solute, water being a common one here. So you can see that the boiling point of water originally is 100. And so for every molal of solute that you add to water, its boiling point will increase by about half a degree. Okay, so that's how you read that table. Melting point of water, or freezing point of water, is 0 degrees Celsius. For every molal of solute you add to water, the freezing point is going to decrease by 1.86 degrees Celsius. Okay, and so again, you can see that how those numbers are not the same depending on the solvent, right? So some solvent is going to decrease or increase by more than water. Some will increase or decrease by less. All right, so let's take a look at this example here and see how we can apply those formulas that we just learned to calculating the freezing point and boiling point of a solution. So we are adding 1 kilogram of ethylene glycol, which has this formula, into 4,450 grams of water, and we want to see what the boiling and the freezing point is. Just a note, ethylene glycol is actually what we call a solution of antifreeze. When you mix it with water, that's what you have in your car. And so we'll take a look at what the result is of mixing ethylene glycol with water. So let's take a look on the right side where we do this calculation. What we want to do is first calculate just the change in the boiling and the freezing point, and then we use those changes to calculate the actual boiling and freezing point of the solution. So to do that, of course, we're going to need to use that formula that I just showed you, the delta TB and delta TF formula. For that, I'm going to need molality, so I'm going to need to calculate the number of moles of my solute, which is just 1,000 grams divided by the molar mass, gives me 16.11 mole. Now I'm going to calculate my delta TB, which is just the Kb times the molality of the solute. The Kb I can look up from that table on the left, and I find that for water, the Kb is 0.512 degrees Celsius per molal, and then the molality can be calculated right here. Again, keep in mind that you got to change that to kilogram for the mass of water. That gives me 1.85 degrees Celsius. That's the actual change in the boiling point. For the change in the freezing point, I would use the other constant, which is the constant for the freezing point from the table on the left. Multiply that with the molality, same molality here. So the change in the freezing point is 6.73 Celsius. So calculating the boiling and the freezing point itself is just a matter of either adding or subtracting. So for boiling point, you will add, and the reason is because the boiling point increases, right? That's why you're adding. And for the freezing point, you would subtract because the freezing point decreases. So when I do that, I get 101.85 degrees Celsius for the new boiling point, which is the boiling point of the solution, and then minus 6.73 degrees Celsius for the freezing point. So you notice why it's called antifreeze, because what this thing does is it makes the solution stays liquid at a lower temperature. Otherwise, water would have frozen at 0 degrees Celsius. And if you're driving in certain parts of the country where temperature goes down pretty low, it might go to -2 degrees Celsius, for example. And then if the liquids freeze up, then of course your car wouldn't work anymore. But if you're able to keep the liquid being frozen at a much lower temperature, so even when the temperature outside is -2 degrees Celsius, for example, your car will still be able to function. Okay. Notice that even though we call it antifreeze, that solution also serves as what we call an anti-boil in this case, right? Because it also increases the boiling point by a little bit. But it's less likely that you will hit that temperature that high during the operation of a car. That's why typically we're more interested in looking at the antifreeze component of the solution and not the anti-boil property.